exam was all about, and why I thought, why I said this paper actually. So it is not just it's not just the question paper. I mean, I wanted some. What is this? Why is it not coming? Yeah, it has come. Can all of you see the whiteboard? Hello?
Yes, sir.
Yeah. So I mean, I'll quickly run through the quiz because otherwise there'll be too many questions of why I got so many marks and why I got so many marks, etc., etc. So I just sort of quickly want to run through the quiz in 5-10 minutes and maybe give some interesting insights into why. I mean, why those questions were given in the first place. Of course, the first question was about non-expression or not obtaining activity and activity of the product. And in the first case, the A was about shake flasks. You get activity, but not in a fermenter. So what really happens in a fermenter? Anybody? Any volunteers? What happens in a shake flask? You get activity, and here there is no activity. So what answer did you give? Any one of you volunteer? You can always volunteer. Your answer sheet is safely there for grading. What is it that you thought would be the possible reason? The whole idea of a quiz or a mid-semester exam is to get feedback upon whether people are understanding what is being taught in the class or not, whether they're internalizing, they're understanding, but whether they're internalizing. Teaching like this online is a very difficult proposition. We have no idea how much of it you are internalizing. What happens in a shake flask and not in a fermenter? So that there is no expression. So there is a 100-liter fermenter. Any answers? Any volunteers? Wrong answers, correct answers? Yeah.
So could I? So like what I wrote was like there could be some problems during scale up, like because when you consider a fermenter, like you have heat generation which basically increases with the volume and the heat transfer rate increases with the surface area. So like there could be problems in the heat transfer during scale up, or similarly for mass transfer or oxygen diffusion.
No. I mean, you see, this is a very interesting. I mean, this is one quality of answer that I will not accept, which is, I mean, I could say the experiment was done incorrectly and therefore it did not come. If experiment was done, so you have to assume that the person who ran the fermenter ran it properly. You can always say experiment was done improperly or there were some mistakes which we do not know that happened, and that is why the result did not come. And please do the experiment correctly and the problem will be solved. It has to be something fundamental. This cannot be a reason for saying that is why our activity was not obtained. So section B, it was obtained here, but not obtained here. This happened, that did not happen. Means, well, you did not do the experiment properly, or various versions of this statement. And what you are giving is a sophisticated version of this statement that, there was some. So the only thing which happens, which you cannot stop from shake flask to fermenter, is that the number of generations, the number of doublings would increase. Number of doublings would increase because it has to grow to 100 liters. From the single clone, number of doublings increases in the fermenter. In a shake flask, you will have very few doublings, and in the fermenter, the cell has to then double, and so the number of generations or the N increases. And I had shown you the plot of plasmid instability of N versus percentage stability, which goes something like this. So it is quite possible that the shake flask culture had this kind of doublings and the fermenter had this kind of doublings, and that is it. So therefore, the percentage stability or percentage recombinance, which is the stability. So stability is something which can drop as the number of generations increase, and then how do you solve it? You can add more antibiotics. You can say that, I gave all the examples. You can stop the early phase from having a leaky expression and stuff like that. So that was point number one. So no volunteers for point number one. Point number two, you see it in SDS page. You see the thing in SDS page, but no activity. So what is the answer you wrote? Well, you saw a false band and SGS page is a good answer. The SGS page result was done incorrectly. What you saw as the protein band, you see the protein band. What, any volunteers?
So the mixture, the components of the mixture inhibit the enzyme activity, and in case of the STS base, we can still get it out, differentiate it.
Yeah, but when I say no activity, I mean no final activity, no activity, which means that somebody will purify it and say, well, I've got the activity now. Wait, the
Sir,
protein
incorrect.
band is, sorry, that's
Incorrect.
again a version of this. Yeah, don't give this version. No activity because it was measured improperly in the presence of other components.
No, protein did not fold correctly.
Correct. So the obvious answer is that the protein was there, but it did not fold correctly. So misfolding is the problem. And that is the most logical answer, that you have a misfolded protein which is not giving activity. It is there, but it is misfolded, usually called inclusion bodies. And what is the solution to this? There are multiple solutions again, and I always expect that you can give any answer. One of the solutions is chaperones. I do not know whether I were told about this, which help in folding. I mentioned this in the class as well, very briefly. One answer is chaperones, another is low temperature, slowing down production, etc., etc. There's so many methods of ensuring that misfolding does not take place, or simply saying that, well, all right, we will fold it later on correctly. We will try to sort of do it in vitro. But if you want to do it in vivo, then you have to ensure that the protein does not misfold. And there are so many factors which ensure that misfolding does not take place. One is using scaffolds, which I talked about, chaperones, which prevent misfolding. Other is slowing down the rate of protein production because the intermolecular interactions stop and the intramolecular interactions become dominant, and so on and so forth. The third was you see the mRNA, but no. So what is the answer to this? You see the mRNA levels. So mRNA is forming, but no. So what is the answer to that? Can you hear me? But no
So the
protein.
translation step is rate limiting, and or the other possible reason can be that the RNA can be degraded.
That is obviously it is great, but why is it not forming any protein at all?
Less
Or
viability
very
of
poor
transfer
levels. Sorry.
less viability of transfer RNA for corresponding codon.
Yes. So the question 2 was the answer to this part. So you say it is a codon biased system. It is a heavily codon biased system, and the transfer RNA is not available. And that brings me to the second question, that one of the possible reasons is codon bias. Something is blocking translation. Most commonly codon bias, but there are other possibilities as well. Yeah.
We also say that the mRNA which is being formed, it is forming like stable secondary structures such as stem loops, and that is why it's not translating.
Yes and no. It is a very, I mean, theoretically possible, but practically almost never, that you would not get any protein. If you have a stem loop structure for mRNA, it reduces the protein. You will get a very reduced protein amount, but because of stem loop structures. But that translation will not take place because secondary structures are not very strong, and so they reduce the translation rates. But yes, you're right and wrong. I mean, I would say that it is a partially correct answer, because it's theoretically right, practically never the case. So now about the codon bias problem, this was an easy maths problem, but the purpose of giving this problem was actually slightly different, and I will come to that in a minute. So did you solve this problem? So I told you there's a 100 amino acid long peptide. So and there are, let us say, X leucines and Y arginines. So all of you, please go ahead. What did you get? And so the codon adaptability index is nothing but a geometric mean of X leucines, which has a frequency of, as I said, the frequency is 15%, while the best frequency is 45%. So that's excess of 0.33. Right, the observed frequency upon the best frequency into some wild alanines, which is arginines, which was 20%, actual alanine usage upon 60%, which is 0.33, and into then everything else is the best usage, so it's 1, 1, 1, 1, 1, 1, whatever till 100, and so the CI will be this ratio of 1 by 100, and that you want to be greater than equal to 0.9. So really it is x plus y. Sorry, the other way around. What the hell am I doing? Sorry, none of you are pointing out. So if we have x, so it is 0.33 raised to of x leucines into, this is a codon bias of 0.33. This is 0.33, 1 by 3. And this is also 0.33. This is equal to 1 by 3. So 0.33 into x into 0.33 raised to y into 1 into 1 into 1. So really we have take log on both sides. So this is actually nothing but 0.33 raised to x plus y by 100 is equal to 0.9, which really tells me that x plus y upon 100 is equal to log or ln or whatever you want to take, log 0.9 divided by log 0.33, which tells me that x plus y comes to 9.5, I think. So you should not have, so x plus y should be less than 10 or should be 9 or less than 9. This is the answer. Did all of you get this?
Yes, sir.
Yes.
So this is easy enough. Now, this why I gave this problem is something that is something to think about, and this is a very interesting question that I often ask. I mean, but obviously this is slightly again beyond the course, but I thought I'd sort of mention it. Is this a good method? Is this indeed a good technique? And that is the question of all averages. All things like CAI, etc., are basically one single point numbers expressing a complex of what is going on here. Now, I mean, let me explain this in a simpler way. Think about it. Say leucine. Leucine has tRNAs corresponding to the best tRNA, which is 0.45. I mean, I'm borrowing from that number. There is another which is say 0.25. And there's another which is say 0.2. Does this add up to? No. Let us say another which is 0.15. So this is what I told you. So 14 plus is 40, 45. And another one which is again also 0.15. Say another tRNA which is say, okay, whatever. Can you hear me and see me? See this board? Let us consider that there are 3 and then there is another which is 0.1 or whatever, and so on and so forth, right? So there are many tRNAs. Now you have the mRNA chain moving here to the ribosomal machinery and getting translated. And the tRNA molecules are coming in here and attaching, and the polypeptide chain is coming out here. Okay. Now just suppose that this mRNA contains a group in this 100 that we gave the answer. There are a maximum of 9 which are allowed of leucine plus arginine. Let us say it was only leucine. So there could be, say, let us say there is a group of 10 amino acids, out of which 9 are leucine. And all of them use this tRNA, which is proportional at 0.25. Your CAI is 0.9. Actually greater than 0.9 because you have only 9 leucines. But if this group of say 10 amino acids contains 9 leucines, all of which require this tRNA, which is available at a frequency of 0.25, what will happen? This will stall. This translation will simply stall. This chain will stop. Because obviously 25% and 9 mRNAs immediately demanded will not be available. As a matter of fact, think about it. If there are 9 leucines, and even if you provide the most preferred codon 0.45 and all of them are this, one after the other, even then, and CAI is actually equal to 1, so you are absolutely fantastic, it will still stall. Because if 9 are coming, you would rather have 2 of these tRNAs and 1 of this tRNA and 1 of this tRNA as let us say for 5. Then at least the possibility that another tRNA and another tRNA, all these tRNAs of different frequencies are actually available. Because if this red one is 0.45, or let us say the green one is 0.45, even this green will get exhausted if suddenly one after the other 9 leucines come in. So you have a CAI of 1, but your system stalls because you should actually use tRNAs in a measured fashion. And that is what the cell does. It doesn't always use this, especially if they're in groups, because this will be exhausted sooner or later. So, and this is not being used at all, but because it is at number 2. The cell would like to use it. Let us say for the first one, it uses the green one, and the second one, it uses the green one again, and then the third one, it will use the blue one, and the fourth one, it will use the red one. Why? Because only then this availability of tRNA is guaranteed. So you see, this is why CAI is a very poor measure. And you can have a CAI of 0.8, but a much better designed system and still get good expression, and a CAI of 1 and not get good expression. Are you getting this argument? Hello? Hello? Hello?
Yes, so we can.
Yeah, so I'm sort of sometimes check that these, so you have to understand, and I want somebody, I mean, remember that the marks are 10 marks for quiz and for 2 quizzes and 120 for minors and what is it, 20 for a seminar or a term paper. Somebody should pick up this term paper and look at CI and why there could be better measures. There could be far better measures of far better measures of this train running rather than just CAI. So you can see that it is this is the problem with averages, that when you take an average, you don't understand the specifics that are happening. So any amino acid that is getting overrepresented in a peptide, it is best to use all the tRNAs rather than just the most preferred one, especially when there are multiple tRNAs available. And especially these amino acids come as a group, because then you would be making better use of the tRNAs. You understand? So this averaging, which is provided by CI, is always a problem. I mean, I hope in economics, and some of you might be reading economics in your spare time, there is something called the Gini index on poverty. Have you heard of this? Of measuring,
Yes,
income differentials. And you can have absolutely, I mean, I can get a Gini index where 50% earn 0 and 50% earn a lot, and I can have a Gini index where, I mean, I can create the same Gini index for completely different income distributions. I do not know whether you're aware of the Gini index. I mean, I'm just drawing this graph for you. I can draw a graph like this, and I can draw a graph like this, and both have the same Gini index. Think about what I was doing. The percentage of population, I mean, do you know what it is? Okay, forget. Let us not get into all the silly things. But my point is that I can recreate the Gini index with completely different income distributions which have the same Gini index and which have completely different social meanings. Okay, so similarly, now the real point here that I'm trying to make is, I hope you do some maths as well, because as engineers, what is the rate at which these tRNAs are entering inside the cell? Have you thought of these things? Or has this been taught to you in biochemistry, some quantitative analysis? Yes, no? Okay. I mean, let us, this is the kind of algebra which you people should be able to do with your left hand. right? Unless you are a lefty already. So, think about it. Here is a cell. This is about 1 micron cylinder. This is about half a micron, or maybe more, or let us say half a micron. Let us assume this is the cell. And you have induced this culture, and the density is 1 approximately for all practical purposes, 1.05, 1.05, whatever, doesn't really matter. And so the mass, and that 50% of the mass is protein. 50% of the mass is protein. And that after induction of recombinant protein synthesis, in 2 hours, let us say, in 2 hours, 20% of the protein is recombinant protein. For good expression systems. Now in 2 hours, remember that this is like an expanding reactor, so it's actually become 2 cells. And so what is the mass now? You know that. So the rate of product formation, so what I'm saying is P is equal to P by V. And so the volume has increased. And the mass, and that at the end of 2 hours, 20%. So that this is, this is 20% recombinant, this is 50%, so 10% of the mass. So P is now 10% of the total mass. So that this is the total amount of cellular mass, from this calculation, that 10% of this is recombinant protein. This has happened in 2 hours. So how many molecules are there in the cell by Avogadro number, because let us take a 100 amino acid peptide, right? So how many, the molecular weight, and therefore how many molecules in 2 hours have been made. And therefore you can calculate how long does it take for each protein molecule to be synthesized. And since it is a 100 amino acid long peptide, how fast does the tRNA train move on the ribosomal RNA? In seconds, or microseconds, or nanoseconds, or milliseconds. I want an estimate. So can you tell me, any of you, do this calculation, tell me next class, what is the time tomorrow? What is the time that each peptide moves? And so what is the time that the tRNA molecule gets to arrive and attach and deliver the desired amino acid? How much time does it get? This is the kind of thing that, as engineers, you should be doing if you want to do good biology, ever. Asking this kind of questions. This is of course algebra, this is not engineering. Engineering would be when you ask that what is the liquid viscosity, and what are the flow rates, and what is the crowding in the environment? Have you studied about crowding, cell crowding? And remembering that it is completely laminar flow, and I hope you understand, because of the low dimensions, that the Reynolds number is less than 1. So life in Reynolds number less than 1. So water becomes, normal water becomes like tar, and solutions become like semi-solids because of laminar flow. So diffusion rates are a huge problem. So how does the cell manage? If you ask these questions now, you will be, I'm deviating, but let us not deviate. And these are questions that I could go on and on, but these are the questions that you should have been asking in your biochemistry course. That what is the rate at which each molecule is being attacked? What is the rate at which transfer RNA is coming? Is it diffusion control? Which brings me to that old problem, which let us not get into this too long. So these are the kind of questions which brings me to this old problem of proteins. I talked about V is equal to V max S upon Km plus S. And the question that you need to ask is, when substrate concentrations are very small, when S is very small compared to Km, then V is equal to V max S upon Km. And remember, just now I demonstrated to you that Vmax is equal to K2 into E naught or E total or E naught, let us call it. And therefore V, or the rate of conversion, is given by K2 E naught or E upon Km. And this K2 is also called Kcat. Kcat is the catalytic efficiency of the enzyme. You remember this? I've jumped quickly. So really, this Kcat by Km, this is the first order reaction constant, right? This is the first order reaction constant because this is into S. So per unit molecule at very low concentrations for per unit protein, whatever this protein is, when it is catching this thing, which is when it is catching the substrate here and converting it into catching it and then and converting it into product, it is the Kcat by Km which determines the rate of product formation per unit protein when substrate concentrations are very low. This is S is very low. Do you follow this argument? Hello? You are gone away or gone to sleep? What? I mean, please put on your mic.
Understand.
You follow this argument? Now the question really is that if substrate concentration is very low, substrate has to diffuse inside. Substrate has to diffuse to the pocket. And so what is the D value of this diffusion? And if diffusion is indeed, if this is rate controlling, remember your relaxation time kinetics, if this is rate controlling, then really it does not matter how efficient the enzyme is, because substrate has to reach the pocket for the product to be formed. So what are the typical diffusion rate constants associated with diffusion of a single substrate molecule to the pocket of the protein, enzyme pocket? And then only product will be formed. And if the kinetics, the protein for rate kinetics, this Km by Kcat is higher than the diffusion rates, then really it is this which will control the V, not this. But you will report it as Kcat by Km, but actually it is being controlled by diffusion rates. So imagine nanoseconds for diffusion and nanoseconds for conversion. Each protein molecule converting the product instantaneously into product the moment it reaches. And it is the supply of substrate which actually controls the rate of product formation, because the substrate has to diffuse in slowly. So there are enzymes where the Vmax by Km values are so high or low? High. Km is so small and that it is actually for all practical purposes the most efficient enzyme. Aconitase is a very good example where actually it is diffusion rather than this which is rate controlling. Now these are the kind of questions you have to ask yourself when I talked about cell, when you start putting in numbers. So not do it blindly. And also understand biological behavior. So obviously the cell nodes cannot evolve to more and more efficient Kcat by Kms, because the observable Kcat by Km will be controlled by the diffusion rate. Are you getting this argument? Hello? Yeah?
Yes, sir.
Yes, sir.
Okay. So these are the kind of questions that I want you to sort of address in your term paper, which I think is very. So what are the rates of diffusion? How do you calculate rates of diffusion to the protein? The diffusion can be here, but then it has to diffuse to the pocket. So there is an additional rate. Can you think of a boundary layer problem where the protein is surrounded by a boundary layer and the substrate diffuses through? What are the typical values of diffusion rates? What are the best values of Kcat by Km that have been reported for enzymes? And so on and so forth. So these are the kind of questions that I want you to answer and think about, and not just focus only on the enzyme engineering part, which is important. And let us get back to it because I have spent so much time. But these are the kind of creative things you need to do. So back to our old stuff, unless you have questions on this. So essentially, you see what I was doing was I was saying that E plus S is ES, and then I was saying E plus P. And the reason I said that I will use the dissociation constant principle, which is ES upon ES, is that this is actually, and then sort of calculate ES, is because it is a very simple task then. You understand? Why? Because what is the velocity of reaction? The velocity of reaction is nothing but K2 into ES. Right? And you also know that the E total which you have added is equal to the free enzyme plus ES. Right? So what is the best essential trick that I am doing here? So I did derive it. Let me sort of do it for, and so really you have to get ES in terms of ET. And that is it. And then substitute it here and you've got your velocity. So so let me do it for a more complex problem, then it becomes obvious. Let us say, for example, we were talking about that problem where there was competitive inhibition. Competitive inhibition really means that that E is not only binding to substrate, but E, not like this, E plus M, of course. Let us say that this was the inhibitor. Let me call it M. Okay, is EM. So E competes with M to form EM, which forms nothing. E competes with S, and so M and S are competitive inhibitors. M is a competitive inhibitor. It grabs hold of the enzyme and makes an EM, which does not make product. So depending on their rates of binding efficiencies, because this here is, let us call it the usual, what would you call it? What did we call it? EI, right? Okay. Or KD or whatever. This is KD. And so now tell me, so now the basic equation is what? ET is equal to, oh God, gone. Can you hear me?
Yes, sir.
Oh, why did it suddenly disappear? Oh, I was playing, but I can't see the display. What is wrong with it? Can you see the board?
Yes, sir.
Yes, sir, we can.
Oh, this pop-up has gone. I don't know why. So you have to keep, I hope, I want to see the pop-up, but anyway, this is not good. So the total enzyme is now, earlier it was divided as E and ES, either E or ES here. Now it is E plus ES plus EM. You get this? So in many ways, the simple argument is that the V, the velocity of reaction, and you think about what I'm trying to say. I'm saying the V by, what is the V max? Can you tell me what is V max? Let me sort of ask you questions because I can't see the board now. Can you see what? Can you tell me what is V max in terms of this? What is the maximum velocity that you can get in terms of K2? It is K2 into ET when ET is the total. Do you follow this argument? What is the maximum velocity you can get when everything, all the total enzyme? Okay, forget it. Then we'll do it slowly. I wanted you to sort of solve it intuitively, but let us say V is equal to K2 E S, right? Okay, and then let me divide both sides by ET. E plus ES plus EM. Okay. Now does it become obvious? because now I will bring, instead of ES, I will bring in ET. And what is E? Come on, from this expression here. What is E in terms of ES or ET or whatever? Hello? Okay, let me do it the other way around. If you don't want to do E, what is ES? I just now wrote it. What is ES in terms of KD? KD is equal to
E is multiplied by S upon KD.
upon ES, है ना?
Yes.
So this part here, this becomes equal to K2 E into S upon KD, ठीक है ना? सब कुछ E के टर्म्स में है. यहाँ पे E प्लस ये ES का क्या होगा अगेन? E into S. I am not going to bore myself. KD. What is this EM? E plus, sorry, E into M upon KI. Okay? Are all of you with me?
Yes, sir.
And now I can take E common, and I'm not going to do it now. I'm bored with this. Please do this. And then tell me what is V. So it is V is equal to ET, which is a measurable quantity, K2 S upon KD. I'm sometimes writing capital into ET divided by 1 plus S by KD plus
M by
yeah, M by KI. Can all of you hear me?
yes, sir.
Plus M by KI. Okay, so this is your expression. And so you see, algebra is simple. You write K2 E into S by E. So instead of writing ES, you bring it in, break it down into E and S. E you keep it as E. ES break it down into E into S, and whatever is it. EM you break it down into E into M by all the dissociation constant logic. All dissociation constant. So anywhere you have the dissociation constant of AB is nothing but A into B upon AB. So always AB can be written as A, and so the same way A and B are E, S, E, M, whatever it is. And so AB can be written as A into B upon KAB, and so you can write this kind of expression and solve it very simply. So you see, this is a very simple solution. And can you now simplify the algebra and write it in the form that I give it to you in the lab practicals? What does competitive inhibition look like? So you have this kind of expression, and using this basic, total summation balance, I can get this value of V. So all of you are following this argument? So can you tell me what is
Yes,
V? Now notice that E1 K2 is nothing but ET K2 is nothing but, oh my, this is really irritating. Huh? I hope you can see this. K2 ET is nothing but Vmax. But that is the maximum velocity, right? K2 into, if everything was Vmax, would be the maximum velocity. So that is Vmax. K2 ET. That is why I told you last class also. And then S by KD. So let us sort of multiply by KD throughout. So we get S and we get KD plus S plus, we're multiplying by KD throughout, right? So what do we get? M KD by KI. So notice M was nothing but the inhibitor and Ki was inhibitory constant, inhibition constant, and M is the concentration of inhibitor. So this is exactly the same formulation that we got for this formulation is exactly the same that I showed you for competitive inhibition. Can you make out for the lab practicals? So it's a very easy derivation because of this oversimplified version that you use, that this is the steady state. Now the more correct definition, so we will be using this kind of model for complex models, enzymatic models, this dissociation constant definition where I can break up, I can write ET is equal to E plus ES plus EM plus whatever I want to write. I can do an overall material balance and then convert these expressions into E into the what? E into S, E into M, and then divide by E and get it. So the algebra becomes rather easy. That is why we prefer this. There is another reason. The more complex, the more correct method also leads to a similar form of the kinetic equation, which I will show just now. So the correct method is to say that the E plus S is ES, and this is going to EP, E plus P, and the correct method, which is also experimentally validated, this is forward, this is backwards, and this is K2, and the correct method is to say that this ES is in steady state or pseudo steady state, I should call it, but anyway, let me call it just as steady state, at a steady state. So DES by dt is close to 0. That is the basic argument. And this steady state has actually been observed in actual experiments. So what do we get if this is equal to 0? What is this equal to? It is actually equal to K1 into E into S minus K2, sorry, K minus 1 ES is K E into S, okay, minus K2 ES again. You follow this? Am I okay?
Yes, sir.
Okay,
Yes, sir.
and this is equal to 0, and this is equal to 0. So really notice the formulation is very, very similar, which says that K1 E into S is equal to now K. Hello, yeah, okay, still on. Is K minus 1 plus K2 into ES. Right. So instead of getting a very, so really in terms of the ES can be found out in terms of E and S as, so ES is now, I mean, you can see that. I mean, it's now equal to K1. Is equal to K1 E into S upon K minus 1 plus K2. There's now a plus K2 term here. You see that the rate equation is exactly similar. You understand this? And so what if this is ES, then this into K2 is the velocity. Right? Hello?
Yes, sir.
So this into K2 is the velocity. And remember that we have to write E in terms of E total. So we have to remember that old equation, ET is equal to E plus ES. E plus ES. So we use the same method now, remembering only that now the relationship between, इसको मैं हटा देता हूँ थोड़ी देर के लिए. Let me remove this. Remembering that ES and E into S now are related not by K1 by K minus 1, which is KD, but K1 upon K minus 1 plus K2. That is all that is changed. So I can you do this algebra for me? Because every time I try to do any algebra, the computer revolts and refuses to let me do it. It says that students should be doing this. So what do we get? Using this basic equation here and this equation here, what do you get? Tell me. Do it on your own. I think I would like you to do it on your own, so that I don't use the board at all. I want the velocity. Essentially, I want ES. Essentially, I want, you understand, I want ES not in terms of E, but in terms of ET. From this, I want ES in terms of ET alone, because then I can write the velocity as K2 into ES. And I want ES in terms of, as a function of ET. Tell me, what is it? What do we get? Just two steps from here to here. Or if you want to do it, I mean, you can write V upon ET, as I told you. The way I did it earlier. V upon ET is equal to whichever way you want to do it, please do it. See, the moment I write, it stops. Any contributions quickly for the class?
So it will be K1 into
हाँ, तो आप
ET.
मुझे थोड़ा सा run me through the calculations for everybody to hear.
Yes,
So from
sir.
this,
So
so ES, what do you get? ES is equal to ES. That's whole of
so-
that's ES, not ET.
so the final expression, right?
Yeah, I mean ETS upon
By S plus K S plus
yeah S plus
K minus 1 plus K2 by K1.
K minus 1 plus K2 by K2 by K2, right?
By K1.
K minus K1, right? All of you get this?
Yes, sir.
Yeah, and then we can get into the same familiar version as, because this is ES, so this into K2 is equal to V, and so this into K2 is equal to V, right? And then notice that this into this is V max, so this becomes equal to V max S upon this now becomes Km plus S. So the format becomes the same. In the earlier case, I had Km being defined as this part only, and now I have it as this plus this. And you can see that the format is the same, and it is really difficult to tease out these variables in a real experiment. And I will not get into this too much, but I would sort of tell you that this equilibrium rates are much faster, and so for all practical purposes, this kind of formulation you can safely ignore and make and do this approximation of this being in equilibrium with this. This is faster, this is slow. So and therefore, what we are trying to say here, not always. So I should be cautious here. So this is the more correct formulation. But we will ignore this kind of correct formulation or correct derivation because we have the same. We have the same kinetic structure with this easier assumption of what I call the fractional saturation. I will now define something. I will end the class here by saying that we will define fractional saturation. The fractional saturation is nothing but the amount of, the amount of enzyme. So this is, so I just now, I showed you the fractional saturation just now. So the fractional saturation, as the term implies, what is the amount of enzyme that is saturated with my, so it is this ES upon ET. You get the point? If the fractional saturation is 100%, then V is equal to V max. Right? If the total protein bound And remember, these are all molar ratios, so don't get worried about the substrate. So what is the fractional saturation? What is the fraction of enzyme which is saturated with substrate, because this is what is going to product, making the product E plus P, divided by the total amount of enzyme that you have added. And this is ES upon, obviously ET could be E plus ES plus EM plus whatever. So this is the fractional saturation. And a definition of fractional saturation directly correlates with the ratio of V and the maximum V max. So now notice it makes sense. Suppose I get rid of this. No, don't get rid of this. Well, keep it. Why get rid of this? So as I increase substrates, this fraction, this E will shift towards ES. So this will become small, this will become large. So my fractional saturation will increase. If I have this stuff here, M here, I can't, again it's gone. Can you hear me, all of you? Hello?
Yes, sir.
Yes, sir.
So as I increase M, and if binding efficiency is hard, then it shifts towards this, then ES becomes small. So you see the fractional saturation and its correlation with V versus, I mean, it's also V upon V max, right? Isn't it? So that is a very simple way to look at enzyme kinetics and using the dissociation constants rather than doing the steady state theory. So I will use the concept of dissociation constants, which is a approximation dissociation constants, rather than the more correct method of saying that ES is in steady state. So instead of the steady state constant, I will simply assume that dissociation constants are correct, derive fractional saturations, and move on to solving the problems. Okay. So essentially the fractional saturation is the ratio of the active states divided by the sum of all states. You understand? So this is the active state and all the other states. Sum of all states ratio of the active states divided by, and this is also, as I said, the ratio of the velocity, because obviously the more the active sites are blocked, the more so all the enzymes are either no active site, nothing is happening. It is blocked by substrate, which is the active site. It is blocked by the active site is blocked by the inhibitor. So you see, it has also physical significance. So let me stop here. And any questions, and otherwise we'll take it up in the next class. So it has more meaning. Fractional saturation has more meaning in terms of understanding enzymatic kinetics. Any questions? Okay, so let us stop here. Oh, it's gone again.
Thank you, sir.
Thank you. I hope it stops.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.